In this video, we'll be looking at the relationship between power, energy, and relating back to current and voltage as previously discussed. Energy is the total amount of work or the total amount of stuff that a circuit has done over a period of time. Energy in electrical circuits is a little bit tricky because we, of course, always have to differentiate between the amount of electrical energy that's being put in by a battery or the amount of energy that's being created by a device. But in the end, for our purposes right now, we're just going to consider it as the total amount of work done by the circuit, like again, cumulatively over a period of time. Power, on the other hand, is not about the total amount of energy used or the total amount accomplished, but more about the amount of energy used per second, or the amount that's being done in an instant. In the example of a light bulb, if we say that energy is the total amount of light produced over a period of time, you can imagine then that if somehow you had detectors on the walls and you collected the light over time and you kept allowing it to pile up, that would give you an idea of the energy. In the meantime, if you looked at just the brightness of the bulb, how much light of it is coming out in this instant, then that would be the power. That's why, for example, a 100-watt light bulb will produce a brighter light bulb than a 60-watt light bulb, where to figure out how much energy each light bulb uses, you'd have to consider how long each light bulb has been left on for. Mathematically, we can recognize that if power is the amount of energy per unit time, then we have this equation, and 1 watt is the unit for energy divided by the unit for time. Now, we want to come up with a relationship here between power or energy and voltage and current. Of course, if we find power or if we find energy, we can use our previous example then to come up with the other one if we know the amount of time. So recall that voltage is the amount of energy per unit charge. Voltage is equal to energy per charge. And current is the amount of charge per unit time. Now, if we combine those two things, or we simply multiply them together, we can see that voltage times current is going to be equal to the energy per unit charge times the charge per unit time. Charge on the top and charge on the bottom cancel out, and we can see that that's equal to the energy per unit time. Now, of course, previously we discussed that power is the amount of energy being used per unit time. So if this is energy per unit time, that's also equal to power. So the voltage times the current tells you how much power a circuit is using per unit time. Now, if we do this sort of normally, if we say that we have, if we have our power or our voltage in volts and our current in amperes, then we can just look at what's really going on here from a unit perspective. Remember that a 1 volt is equal to 1 joule per coulomb, and an ampere is equal to the number of coulombs per second. And so we can see that 1 joule per 1 second is still equal to 1 watt, the unit for power. If we look at the energy formula, I'll just start with the equation I gave previously, that power is equal to energy per unit time, and we rearrange this so we solve for energy, so power times time, and then we look at a very simple problem where, let's say we have a 100-watt light bulb being left on for 5 hours or something. Then if we convert that 5 hours into seconds times 60, so 60 minutes in an hour and 60 seconds in a minute, 300 times 60. That's 18123 seconds. Then our total amount of energy here is going to be 100 times 18000, which is 5 zeros. And what we can very quickly see is for a 100 watt light bulb on for a 5-hour period, we already get a pretty unusably large number for the amount of energy that's being used by that circuit. If we imagine trying to figure out how much money we had to pay on our electrical bill in this way, we'd see that it would very quickly become, the numbers would become very much too large. So for energy, an alternative unit that they use is the kilowatt hour. This is just your power, but instead of being measured in watts, you would use it in kilowatts, and your time, but instead of using it in seconds, you just leave it alone in hours. In the same example, where we had a 100 watt bulb, which would be equivalent to 0.1 kilowatts, and a 5-hour time period, we would get 0.5 kilowatt hours. And that just makes a much more usable unit for energy when considering the amount of energy that might be used in a typical household. So that's power and energy and how they're related to current and voltage. Again, numerical practice is available in the PowerPoint associated with power and energy.